All right. So let me do several clarification. I mean, there are too many questions here, so I will arrange some others next time, but let me quickly go through the things here. So actually there are some of you are asking about like actually this one we call it sector. And for like let's make it clear. Sector 3 is a sector and sector 19 is a sector, but sector 3 looks quite larger than sector 19, right? So actually there are two different kind of hard disk drive. I mean, there are some more advanced one. For some more advanced one, their outer tracks will not be the inner concentric with the inner track. For example, because sector 3 is larger, so they will do more finer cut here. So actually sector 3 will become three or like two sectors here, like sector 3.1 and sector 3.2. Okay, so this technology is called zone bit recording, or ZBR. You can go to find the ZBR, and this one is about. But the thing is like, because you need to partition the outer track to more sectors, so you need some management here. So it depends. I mean, if you are going to get a simple one, then you can just waste some capacity, but you don't really need to care about like what is this. I mean, like for this sector 3, you only need to read one sector out. But for example, if you are going to get more capacity, then the way is you're going to partition this sector into more sectors, because larger than one sector. So it is possible to support two sectors. Okay, but you may need some management to manage about this. What is the data stored inside? Okay, so this is for the capacity of the sector. And I think I didn't really make this so clear here. So let me quickly go through it again. So actually, this read head, they are using the GMR technologies. And then you can think about this read head is always like, I mean, when the hard disk drive is powered on, there is always the power sent into a GMR. So you always can get the voltage value. You will always get a voltage value for GMR here. And the thing is like this. If this read head quickly go through this recording medium, and this recording medium will sense the free layer, right? In this example, because the electric field is from N to S, and then the free layer here now, the N will be on the left-hand side, S on the right-hand side. So the electric field will go this direction. So according to the characteristics of GMR, if the fixed layer and the free layer, they are in the different electric directions, then this GMR will become high resistant. Okay, so if it has a high resistance value, so as I mentioned, like there is always power on, so there is always a voltage. So according to the Ohm's rule, voltage equals resistance value times the current value. So actually, if you always give the voltage value and then you have a high resistance, you can receive a lower current value. So GMR here will return a lower current value to the controller of the HDD. So in this case, if we get a low current value, we can know, oh, actually this one is in this direction. I mean, the electric field is in this direction. Okay, so at the same things, if GMR goes to another recording medium now. So if the recording medium is the N is on the left-hand side, S is on the right-hand side, then we will sense the free layer. So once again, since the free layer will become this direction, and because the fixed layer is using the permanent magnetic, so it always will go for the same directions, just on the left-hand side to the right-hand side. And then for this GMR, it shows the low resistance value. So again, the same thing is because the GMR is a power on, always power on. So the voltage, it will always get, you also give the same voltage value. But because this is a low resistance, so this GMR will return a higher current than the left-hand side. And the higher current when when the controller of the hard disk drive receive this larger current value, then the controller will know, okay, so this one is in the opposite of the electric field from right-hand side to left-hand side. So in this case, we can read out the data. Okay, so there's a small things here. Actually, for each of the recorded medium, there is a gap here. So the gap here, there are several kind of functions for this gap. The one is because there are different kind of electric fields for the recording medium. So we don't want one recording medium to affect the others. So we need some physical distance between this recording medium. So I mean, the distance, if the distance is larger, then the magnetic force will become weaker, will become lower effect on others. So what is the distance for the two recording medium? It should be finally calculated by the HDD vendor. So there are another aspect is about when the recording medium goes to when the write head goes to the recording medium, and because the write head is quite large, so the magnetic power is also huge. And if there is no gap between these three recording medium, it is possible the write head will write to this recording medium or this recording medium. Okay, so then there will be an error. So this is the reason why there is always a distance between all recording medium. Like we can avoid the influence between the neighbor recording medium, and we can also alleviate the effect from the write head. Okay, so this is for the HDD. And let's keep going on for the SSD. We stop here, right? We were saying like why there is if there is a electron inside the floating gate, then you use a V-read, the current cannot pass through this structure. Okay, so the reason is like this. This is a little bit electric, but yep. Okay, so for the program, we push the electrons from P subtract into the floating gate. So this is a P subtract, and we are going to push the electron inside the floating gate. But how to do these kind of things? So like this, as we say, this one is word line. So we will apply a high voltage on the word line. You can imagine this is a 20 volt and this is a 0 volt for the P subtract. Okay. Okay, so because we are using a super high voltage called 20 volt, so there will be a lot of delocalized electrons to be generated on the P substrate. So delocalized electrons is called like 游离电子. Okay, so if you give a super large voltage value and there are more delocalized electrons will be generated. And if this voltage is kind of way smaller, like 10 volt or like 5 volt, then you will get fewer delocalized electrons. So it depends on how large this voltage value is. Okay. Okay, so actually, if you give the high voltage value, the delocalized electrons will be so excited. So if you get enough energy, it is possible for this kind of electrons to pass through the electrical insulator. So actually, in the more kind of technical details, actually there is a called tunnel effect. I mean, if you give a large enough of the voltage value, you can get a higher electric field. Then it is possible to generate a tunnel from this kind of dielectric layer. Then the electron will pass through this tunnel into this floating gate. So the key thing is about the voltage value, how large it is. If it is large enough, then you will get a lot of delocalized electrons. You will make them so excited, and then they can pass through, they can cross through the dielectric layer by using the tunnel effect. Okay, but I mean, those will not be on your final. I mean, I will not ask you about what is the effect for these kind of things. Just want to let you know how the electrons can get into the floating gate here. Okay. So in this example, how to read out the data. So actually, we are going to use a relative low voltage. So for example, if this is a voltage called 2 volt, okay. So because this is only 2 volt, so there are very few delocalized electrons will be generated on this P substrate, right? Because this is only 2 volt, so there's only 4 electrons here. Okay, so in this case, actually the 2 volt is not high enough for creating this tunnel, and these electrons will not get enough of energy, so it will not be that excited. So actually, those electrons cannot cross through the dielectric layer into the floating gate, and then they will be kept on this N source and N drain. Okay, but But the thing is, because there are too few of the localized electrons, and if you are going to create a current, then you need more enough of electrons, because the current means there's a lot of electrons that are moving. So moving electrons can lead to the current. But if there's no enough amount of electrons here, and there is not enough of energy to let them move, so there is no current between N source and N drain. Okay. Okay, but there's another example. I mean, we use 2 volt. Okay, actually, when we're using 2 volt, actually we can get this amount of delocalized electrons. But why when we use a 2 volt, like the left hand side, we can only get 4 electrons here? The reason is because before reading, we apply a higher voltage value. So they generate too much of delocalized electrons from using a 20 volt. Okay, so you can think about if you use a 2 volt and then if you don't do the program before using the read, actually you can get that much. But because when you apply a 20 volt before you are going to read the data, then some of the electrons will be captured inside the floating point. Okay. So in this case, if you use 2 volt, actually these electrons, the same things, just 2 volt is not like high voltage enough. So the electric field cannot be strong enough to capture the electrons inside the floating gate. I mean, there is no tunnel here if there's only 2 volt. And then the electrons will not be that excited. So in this case, the electrons will be collected at 2 ends from N source and N drains. But because there are enough number of electrons, so actually there will be some current generated between the N source and N drain, and then we can get the current from the end of the bit line, because this is a bit line, so we can say like, hey, we know there is no electrons inside. Okay, so actually 2 volt is about we need to finally calculate it. We need to calculate about how much of electrons there are around when you are using the 2 volt. So I mean, those parameters, they should be fine-tuning when the SSD vendor is going to generate the SSD. Okay, so higher voltage values include more electrons. What I mean is about if you apply a higher voltage value, more electrons will be delocalized from the P substrate. Okay, and the number of excited electron is correlated to the voltage value, so larger and more. Okay, and smaller voltage value, you can only get fewer. But the thing is, if you first give a super large, like voltage value, and there are too much of the electron be delocalized on the P substrate, then after that, if you give a smaller one, you will get way fewer electrons from this case. So in here, there is no current. But here, even you use a 2 volt, but if there is no electron inside the floating gate, you can get the current from the N source to N drain. So this is a way to program and read the NAND flash cells. Okay. So is it okay for this part? All right. So another example, if we are going to remove electrons from the floating gate, then how to remove it? So like this, we should apply a negative 20 volt from the P substrate, because if we apply the negative 20 volt from here, then the electrons will be dragged out from the floating gate, because 20 volt is quite like a large voltage value. It will create a strong enough of the electric field. So in this case, the electrons inside the floating gate will be excited, and then it can be dragged out from the dielectric layer and to the ground. Okay, like these kind of things, you can drag out the electrons out, and then there will be no electrons inside again. Okay, and the cool thing is about actually the P substrate. You can think about P substrate connects a lot of cells, because for all the NAND flash cells on one P substrate, it means they are all belonging to one block. Okay, so all the memory cells in one block, they share the same P substrate. So this is the reason why we just mentioned when we are going to erase the data, it should be in the block granularity. Because when you are going to apply a -20 voltage on a piece of track, it means you are going to apply the -20 voltage on a block of the memory cells. Because they all share the same piece of track. So if you get a -20, then all the memory cells in this block to get the O -20 volt. So they will drag out all the electrons for all the memory cells sharing this piece of track or like sharing the same block. Okay. So a quick recap, like if there is no electrons inside the floating gate, then we say this is the voltage value, and we say probably it represents 1. And if there are many electrons inside the floating gate, then it means like the high voltage value. So the program is to push the electrons from P substrate into the floating gate, and then erase is to drag the electrons from the floating gate out to the P substrate. Okay. Okay, so I think there's one cool thing to let you know. Actually, this one, we say like, if this is a low voltage value, we say this is 1. And if this is a high voltage value, we say this is 0. And actually, 1 and 0, I mean, you can define by yourself. So the key thing is just about there are 2 stats. You can code it the left-hand side 1 and the right-hand side 0. And you can also code it the left-hand side is 0 and the right-hand side is 1. So it just it depends on the definitions of different programmer. Okay, so this can be, I mean, configure as you want. Okay, so let me give you a overview example here, because before this patch, I mean, here we only focus on 1 bit, right? I mean, there is an electron inside or there is no electron inside. So it means the scenario of only 1 bit. But we say, actually, SSD should work in the patch granularity when we are going to rewrite the data. So the example is like this. If this is called patch 1, and patch 1 means all these kind of memory cells, they share the word line. And patch 2, they also share the word lines. Okay. So when we are going to program the second word line, or like patch 2 to 1100, and for example, if now it is 1111, okay, 1111 means, if we use this example, 1111 means there's no electrons inside the floating gate. So when we are going to program to 1100, it means we are going to push the electrons for the later 2 memory cells. We are going to push the electrons from the P subtract into the floating gate. So we are going to make the floating gate there are some electrons for the last 2 memory cells. Okay, but actually 1 and 0, it is what we human beings, what we are thinking about. But actually inside the SSD, the only thing is about voltage value. So 1 means low voltage value. So usually it is around like maybe 1.9 volt or maybe 1.8. So it depends. So for example, we assume like for bit 1 means 1.9 volt. So actually they're all 1.9 volt. And then we say for the program, we are going to apply a super huge voltage value on the word line. Okay, so when we use 20 volt, when we apply 20 volt on the word line, we mean we are going to program this patch. Okay, and then we will send the path like 4 volt to pass through all other if we are not going to program them. So the reason is like if we can use the 5 volt, we can protect the effect from the 20 volt. Because if you apply 20 volt here and the electric field is strong, so it is possible to influence the other data on other kind of patches or other word lines. Because actually, when you are designing this kind of circuit, actually they are very close to each other. So we need this kind of protection voltage to protect those other non-program memory cells to be programmed. Okay, and we need to involve another concept. It's called inhibition. So inhibition is about inhibit those, because we say we are going to use program 20 volt to do program. So if there is no inhibition, all the memory cells will be programmed, right? Because 20 volt here, so all the memory cells will will get programmed. The electrons will be moved from the p subtract into the floating gate. Okay, but with this inhibition voltage to apply on the bit line, actually we will not program the first two. We only program the last two one. Okay, so you can see now the last two memory cells becomes 3.1 and 2.9. It means the electrons are moved from the p subtract into the floating gate. Okay, so what does this kind of inhibition mean? So like this, we say we apply 20 volt on the wall line. Okay, so this one is this one, the wall line. I just rotate in an angle. So this is 20 volt, and then this is 0 volt for p subtract. And the bit line, if we use the inhibitions, it means we apply a 5 volt inhibition here. Okay, so what does it mean? If we give a 20 volt, then there are a lot of electrons be excited. Those delocalized electrons, generally it should be moved into the floating gate, right? But the thing is about, because here is another direction of the electric field, there is a 5 volt of the electric field here. So when the localized electrons is going to cross through the accelerator, because there is an horizontal kind of electric field to do the interference. So actually the electrons is hard to cross through the dielectric, because here is another field to generate here to do the interference. So this is how the inhibitions works on preventing those kind of memory cells being programmed. Okay, so with this inhibition voltage, we can prevent those floating gate that should be programmed. Okay, so in this case, the first two memory cells can still stay in the low voltage stage for their floating gate. Okay, so those are about right. And in this case, like you can configure the inhibition voltage value, and then you can write the data in one patch. Okay. So how about to read out the data? So read is like this. We are going to apply a 2.5 volt here. And the same things, we will apply a higher voltage called 5 volt for all other kind of patches that we are not going to read. Okay, so the reason is like this. If we apply the 2.5 volt here, okay, so if you still remember, 2.5 volt will let the p subtract to generate a few delocalized electrons, right? But the thing is about, if the floating gate, there's no electron inside the floating gate, then 2.5 volt is enough to generate the current to pass through this floating gate. But on the other hand, if there are some electrons already inside the floating gate, then 2.5 volt will generate way fewer electrons from the p substrate. So because there are too few of the electrons, it cannot generate the current. So like this. So the current will stop here because there is no current barrier. There is too few of the electrons. So current will stop here and you cannot go through. Okay. So the reason for other patches that they are not going to be read, we give a 5 volt is because if you use 5 volt, then the delocalized electrons from the p subtract will be way more than 2.5 volt, right? So for 5 volt, no matter there are or there are not electrons inside the floating gate, definitely there are electrons. Sorry, there are current path through. Okay, so like think about like these kind of things. So if we apply a like 5 volt or even more than 5 volt here, so there are a lot of electrons to becomes excited. Okay, but 5 volt to like 20 volt, because the energy is still not enough to let them to cross through the dielectric layer. So those kind of delocalized electrons will be collect from the N source to N strand. And because 5 volt is so high, so there are way enough of the electrons can generate a current and can pass through from end source to end drain. Okay, so this is the reason why they're using a higher voltage value to that other patch to become all-green to pass the current. So in this case, what we are going to do is we are going to sense at the end of the bit line to say like if there is if there is current values to be detected at the end of the bit line, then we can say, okay, so these memory cells, there is no electron inside the floating gate. But if we cannot receive the current from the end of the bit line, it means there are some electrons inside the floating gate. So you cannot generate a current. So the current cannot pass through this point. The current will stop here. Okay. So this is the way to read out the data in a patch granularity. Okay. Okay. So I think you already know, like, because when we are going to use the erase operations, we should apply on the P subtract, and for P subtract is all memory cells belonging to the block will share the same P subtract. Okay, so erase should be in a block granularity, and because erase is larger than write. Okay, so when we are going to update the data inside one patch, what we are going to do is erase before write. Okay, because for write, we can only increase the number of the electrons inside the floating gate, right? We cannot drag out the electron inside the floating gate. So write can always only write one times. And if you are going to erase it, then you are going to erase a block. Okay. So usually people will not really do the update in place. Usually people will do out place update. Yep.
这里用 NMOS 做是实际上都是用 NMOS， 但是会用 PMOS 做距离，会用。
Based on understanding, usually people are using PMOS. Yeah. Okay, so this is the NAND flash blocks. Like the same things. This is one NAND flash patch and one NAND flash patches. So actually, for one NAND flash patches, there are several bits here because they are 4 kilobytes. So there should be 4 KB amount of the bits here. So now, if we are going to modify, if we are going to adjust the bit from 0 to 1, or like from 1 to 0, actually, we cannot erase and write only one patch. And the reason is we should erase the whole block. So it is not effective enough if we are going to only modify one patch and we are going to erase the whole block, because there are 512 patches in the block. So a better way is to, just like SMR, the better way is to just mark them as invalid, and then to write a new patch to other place. So the methodology is called read, modify, write. We read out the old patch, modify them in the memory inside the SSD, and then write to a new patch. So in this case, we don't really need to do the erase. We just move the old data, modify it, and then to a new position. Okay. So that is for write. And let's talk about some interesting things, because when you are going to the market to buy an SSD, usually you will hear a lot of terminological like MLC, or like there is kind of TLC, QLC, these kind of things. So the concept is like this. Is it possible to let a cell represent more than 1 bit? So in this case, if this is a 2 bits MLC, 2 bits multi-level cells, inside the floating gate, there are 4 states. So for 1, it means there's no electron. And if there are 1/3 of electrons, then it is called 1, 0. And 2/3 is called 0, 1. So if there are a lot of electrons inside, it is called 0, 0. So as you know, it is possible to say if you have a triple level cell, there's a 3 bits MLC, TLC, then it means there are 2 to the 3, they are add states here. So for S stats, you need to finally cut the stats of the electron into into 8 different states. Okay, so no electrons, and then 1/7, 2/7, 3/7 of electrons. But it is possible because now if you're going to buy the SSD, now people are using the quasi-label cells SSD. So there's a 4 bits per cell. Okay. So this is about the MLC. And the right-hand side is more details about what do I mean for 1/3 of electrons. So like this, if this is stat 1,1, then there is no electron. And then if there are electrons inside, so there are 3 different cases for electron. There is very few electrons, there are middle amount of electrons, medium amount of electrons, or there are a lot of electrons inside. So it represents different stats and different voltage value for the floating gate. Okay, so you can image like if this is a TLC, if this is a 3 bits MLC, triple label cells, then you need add stats to represent it. Okay, so the challenge is about because you need to finally control how much of electron inside. So you need more time to do the program. You need more time to do the write operation. And also you need more time to do the read, because if you only have a single label cell, you only have 1 bit, then it is quite easy. You only need to decide, you need to judge about if this is like with current or without current, right? But if in this case, you need to try a lot of reference read to check about what is the state now. So usually if you are using the MLC, only 2 bits, usually if you look at a spec, the read time will be 1.5 to 2 times like longer than the single bit label cell. So actually now most of the SSD you can get a larger, cheaper size than like 10 years ago. But the things you sacrifice is the read time, the write time. So the read time and write times become slower and slower for this kind of new SSD, but you can get more capacity there. Okay. So this is the case. And there is another kind of characteristic of SSD is SSD usually has limited lifetime, or like there are a lot of errors occur in SSD. So there are several errors here. First of all, let's talk about things called retention errors. So retention errors means a cell cannot permanently retain electrons. So electrons as kept over time. So it means like you store the data in these cells, and maybe after 2 years or 3 years, you don't do anything on that cells. And then maybe 2 years or 3 years, it is possible the electrons will try to escape from this cell. Okay, so this is called retention errors. So there are a lot of research on this kind of things because like if you look at this figure here, the x-axis codes the x-axis indicates the PE cycle. So the PE cycle means like how many times you program the whole SSD and you erase the whole SSD. So PE cycle 1 means you write a lot of data in this SSD. For example, if this SSD is 1 terabyte, you write 1 terabyte of the data into the SSD and you erase the 1 terabyte of the data. Then this is called PE cycle 1. So PE cycle 2 means like if this SSD is 1 terabyte, then you write 1 terabyte data inside and you erase the 1 terabyte data. And you write another 1 terabyte data into this 1 terabyte SSD and you erase it again. So PE cycles as the x-axis and the y-axis is the bit error rate, just like how many bit errors among these numbers. So for example, if here is a like 10 to the minus 4s, mean there is 1 error among 10,000 bits. Okay, so higher means bad or worse. Lower means good, because lower means there is only 1 error across 10 to the add of the bits. So the error is lower. And like 10 to the minus 2 means there is 1 error among every 100 bits. Okay, so the error will be super high. And 10 to the 0 means like all bits they are error. So it is go 10 to the 0. So you can see actually different lines here means about like 3-year retention. For for the red line. Just like if we put the SSD there for 3 years and we don't do anything, then how much errors there are. So for this, the top red line here, for 3 years retention, you can think about if we first write and read the SSD for 100 times, because this P cycle is 10 to a 2, is 100, right? So we write 100 times of 1 terabyte data, and then we erase 100 times, and we stop, and we just put there for 3 years. Actually, the error rate will be 10 to the minus, I think this is 6. And then if you read and write more data into the SSD, for example, if the P cycle climbs to 10 to the 5, then the error rate will becomes like 10 to the minus 2, or even more serious. Okay, so what is the reason like this? So the reason like this is here. One moment. Okay, hold on, this one. So the reason like this is actually dielectric there. This is a thin accelerator, so there is a lifetime for the dielectric. If each time we apply a strong voltage value to let the delocalized electron to cross through the dielectric, so the dielectric will becomes thinner and thinner. And one day, if the dielectric there is not enough to capture the electron inside the floating gate, then this is called wear out. Cool. Okay, so you can think about, because we say we are going to use 20 volt to program this cell, and 20 volt, it will make the dielectric there to becomes, there's a tunnel, right? So we change the form of the dielectric there. And then this one will hurt the lifetime of dielectric there. I mean, if you only program 1 to 2 times, it doesn't really matter. But if you program like 1,000 or like 10,000 times those kind of things, then the dielectric there will become thinner and thinner. And if one day it cannot, if one day there comes electrons, it is possible to escape from this dielectric layer, then the bit error rate will climb. I mean, when it becomes thinner and thinner, it will not be like all the electrons can escape at the same times. But it is like for every maybe 1 day or 2 days, maybe there are 1 or 2 electrons will escape out because there is some natural effect there. Then this is called a wear out. Okay. So coming back to here. So retention is just about, because you just put there and you don't use the SSD, but the dielectric is a kind of it's kind of the subject there. It's kind of the object there. So if you put there for 1 or 2 or 3 years, and this object will becomes, the retain capability will become lower and lower. Okay, so one day it is possible to become 2 things, and then you cannot retain the electron, you cannot capture the electron inside. Okay, so actually people doing some kind of analysis on this kind of error. So like this, when you are using an MLC or like 2 bits SSD, most errors are from 00 to 01 or 01 to 10. So it means 00 to 01, 01 to 10. So they occur in the higher bit rate, in the floating gate with the higher voltage value. So the reason is about for the 00, because it has a lot of electron inside. So it is possible when there are more electrons, it is possible to escape some of them. And if some of them are escaped, and this state will be jumped to level 2. And then for level 2, when it puts for a relatively long time, it is possible to jump from level 2 back to level 1 if there are some electron escape. And the reason like it is not possible from level 1 to jump to level 2 or level 2 jump to level 3 is because for level 2 to move to level 3, you need to insert more electrons into the floating gate. But if we are going to move the electron into the floating gate, usually you need a higher, larger electric field to capture the electron to move it from the P substrate to into the floating gate. Because if there is no strong enough of electron, if there is no strong enough of the electric field, P subtract will not be generative enough of the delocalized electron, so it would not increase the Fullerton gap. I mean, increase the number of the electron inside the Fullerton gap. Okay. Okay, so this is the things I say, like, hey, if you have higher P cycles, means you program and erase a lot of data here. So these layers will become thinner, and one day it is not able to retain the electrons. And then actually there are two different ways to estimate a lifetime, because we need to know like what is the health status for this patch or like these blocks. So there are two ways. One is called PE cycles, another is called bit error rate. So what I say PE cycle is more implicit is because, as you know, like if you write and erase more data, then most of the cells, their dielectric will become thinner. But because different cells, they have different dielectric. So by nature, it is hard to predict. For example, we only know for this patch, it is write and erase for a lot of time. Maybe some cells, the health status for some cells is bad, but maybe for some, maybe it is super healthy because there are some process variations between different cells. Some cells, maybe they can endure more kind of write and erase, but maybe some cells, they have worse health status because their dielectric layer is easier to be thinner. So PE cycle is implicit. It only can give you a big picture about like if you have a higher PE cycles, then probably the lifetime is bad. But for each cell, it is hard to say because cells have their own health status. So not all the cells that share the same health status. So if you are going to know for each cell what is the health status for each cell, I mean how much of data we can still retain, then bit error rate is a more exact number. Just like each time when we read the data from the SSD, from the nameplate cells, we can check their bit error rate. We can know what is the exact status now. Is it kind of very close to prone to error prone, or like maybe no, there is not that much of error now. So for each bit error rate, if you read out the data and you find like, hey, this cell have more error, it means this cell is going to be worn out maybe recently. And if you read out the data and the bit error rate is super low, that means like this cell is super healthy. Okay. Oh, one more thing. And actually MLC or like TLC, QLC, it has more serious retention errors than SLC. So the reason is because you see like here is the voltage value, right? So we are going to store more different status inside this kind of Fullerton gap. Okay, so for this, if the reference value here, there are three reference value. So it is possible, like for this L3 stat, it slightly move across the reference 3 line, then it will be misread as level 2. Okay, so if you split the status into more kind of, if you are using the 3 bits, 4 bits, then it means like in the same Fullerton gap, you need to represent more status. Then it is possible to increase the error rate because only slightly difference from one voltage to another voltage, it will be misread as maybe level 2 or level 1. So more stats, it means like more error will be generated easier. Okay. So here is a kind of overall picture for SLC to QLC. Like P cycle for SLC is super long. It is around, it can be more than kind of a million. But MLC, TLC, and QLC it drops a lot. So it's, for example, for TLC and MLC, maybe it's kind of several thousands. But for QLC, in some cases, it can only endure for 500. Okay, 500 to 1K. Okay, so it is quite poor. But the capacity for a QLC is super large because you can see like the bit per cell, you can store more bits in each cell. Okay, and yep, that's it. Okay, so let me put together for SSD architecture here. So below a device driver, there's SSD. So inside the SSD, there's controller, and there's DRAM, and there's NAND flash chips. So today we focus more about how to read, how to write the data from the NAND flash chips, and why we should read in the patch size, why we should erase in the block size. And actually, inside the DRAM, we store things called translation table, and we will talk about it next week about why we need this kind of translation table. And the translation table actually looks very similar to patch table, but there are two different things. Okay, and also we were talking about the controller things, about why we need a CPU inside the SSD, what kind of things that we are going to control inside the SSD. All right, so there's time, so let's call it a day. Thank you, guys.